Howdy y'alls, it's the Diabolic vtutor, and we're back here with log functions yet again. We're going to cover the, I guess, miscellaneous cases, or rather the non-main bulk of it, basically covering the natural log, and then we'll also cover the change of base rules, which we kind of ignored for the previous streams. So let's get started for that one. Okay, so we have the idea of the natural log. It's basically when you see this particular form right there. So we're used to seeing subscripts for our logs. So for example, you see log subscript with a 2 of x is equal to 8 is equal to 3, for example. So in this situation, this is log base 2. And then we've already talked about the invisible numbers. So if you have log with no written subscript, and that is equal to something like this, then for this particular situation, the invisible number is invisible number 10. Let me put that in a different color. So that's implicitly, it's supposed to be a 10 right there. And then now we have the natural log. So we have something, it's written like this. So in this situation, there is also an invisible number right there. So if you want to think about it this way, you can. The natural log, you can think about it as just simply log with the base invisible number base e. Something like that. So for all intents and purposes, this thing right here is the same thing as that thing right there. So technically nothing new for the situation. It's just understanding that there is hidden notation. This is like a specialized case. And you might be wondering, what is this? What is that e exactly? So the e is something called the natural number, I think. It's something like, it's approximately 2.72 ... It's going to be an irrational number, very similar to something like pi. So let's write that down real quick. Similar to pi. So there's pi, classic pi. Pi is approximately 3.1415, etc. I think it goes up to 9, and I forgot the rest. Well, I mean, technically I can't remember the rest because it goes on forever, but this is the most I've ever memorized. I always found it unnecessary to memorize more than that. But up to here is sufficient. Up to there is also pretty good too. Alright, so this one is an irrational number, as is e is also irrational. There's like a special derivation for this one, I think. There's like some sort of limit that you can work to get the natural number e, but I forgot what it was. But this number, just understand that the natural number, the e is approximately 2.72. So it's just similar to pi, that it's irrational and it seems to show up a bit in mathematics. So it's kind of important. And that's it for the natural log notation. Very easy, right? Okay, so let's just do some example problems for that one. So if we have e to the power of 3, and that is equal to something like 2 to the power of 4. In this particular situation, wait, there's no letter. There we go. There's a variable now. So in this situation, don't be fooled into looking at this e and thinking that it's some sort of variable. It is not a variable. It is just a constant, 2.72, etc. for this one. So again, it's similar to something like having pi cubed is equal to 2x. So if you have the second scenario, then those two, this term right here is just a constant. It's pi to the power of 3. That's a fixed number. This one has your variable, and then this one is a fixed number. So when you're doing something like this, you want to basically free up the variable. All right, but that's not what we're doing. We're doing this similar problem right here. And again, this one is just a constant. And of course, the trick that we have to freeing exponents is to simply take the log of both sides. Now, which log would you like to take? You could basically take any log you wish. You can do log base 2 if you really want to. You apply the log base 2 to both sides. meaning to here and to there. Or you can apply log base 3. This is not the most optimal one to choose, but you can also choose that and apply the log base 3 to both sides. You could even choose log base invisible 10, which again isn't super optimal, but it's perfectly fine. So my preference is to use natural log and apply that to both sides. So that's what I'm going to choose to apply to both sides. And the reason why I choose natural log is for a very simple reason. It only has 2 letters to write, right? So you only need to write L and N, and then that's it. Versus if you have to take log base 2, for example, you'd have to write LOG, and then you'd have to put a 2. Too many letters, right? So this is just my preference. You could pick whatever log base you wish. I'm going to do my preference first, and then I'll show some other examples regarding other log bases that you can choose. So we're just going to apply this natural log to both sides. So applying it to here without immediate simplification, we get that one, and then you apply the natural log to the other side. Don't call it multiplication. It's not multiplication. It's just applying the function, the natural log function, to term on the left and then term on the right, thereby getting that result. Okay, so for this one, you just take this exponent 3 and then you could slam dunk it in front. Classic move. Same thing, we can do the exact same thing here, which is why we're taking the logs of both sides. We can take this exponent, which is the letter we're trying to solve for, and slam dunk it in the front, so it's now very nicely in the front and more easily workable. Take a step back, of course. Remember, this is not an unknown. This is a known value. This is a constant e. So this whole value is a constant. This is the letter we're trying to solve for, and then this one is also a constant. So to solve for the letter that we care for, we just need to clear a natural log of 2 from both sides. It's a very simple operation. Just divide both sides by natural log of 2, natural log of 2. Cancel, perfect. And thus do we get x is on the right hand side, and then left hand side, I'm just going to move it over here. We're going to get 3 times natural log of e all over natural log of 2. So that's the answer right there. It's not the best looking answer because this is simplifiable, so let us simplify this. So how come we can simplify that? Well, don't forget this ln, that's natural log, so that's, in a way, we're going to rewrite this as log base e, and then the argument is e. And I really emphasize to recognize these forms. When the log base matches the argument, you can just simply cancel it. It becomes 1. Or if you don't care for such memorization, e to the power of what yields e? Well, anything to the power of 1 should get it itself, right? So thus we can cross this out, and that just becomes 1. So final cleanup, we have x is equal to 3 over natural log of 2, and then we're done. Not the most beautiful looking answer, but it's pretty good. It's good enough. Yeah, so this one, you just leave it as such, or you can punch it, well, no, don't punch it into your calculator. Teachers, to my knowledge, almost never want to have the approximate form, so this is exact form, so let's leave it as exact form, which I think is better anyway. Alright, so that's if you are lazy like I am, and then you choose to just apply log to both sides. Again, this is not multiplying both sides by log, okay? This is applying the log function. So it's similar to something like this. If you have x cubed is equal to 28, for example, and then you can apply the cubic root to both sides. We're not multiplying both sides by the cubic root. We are applying the function to left side and then right side. So that's what I mean when I do this parenthetical with the natural log right there. We're applying the function to both sides. Not multiplying, not distributing, okay? And then this one right here, this problem, or once we change it into this, once we go from this form to that form, it's doing a problem that's similar to something like 3 times 8 is equal to x times 2. Okay? This is a constant, like how that's a constant. That is a constant, just like how this is a constant. That's a constant times the letter that you're trying to solve for. Constant times the letter you're trying to solve for. So you just want to clear the 2 from both sides, so divide by 2, divide by constant 2 to clear that, and then you will have solved for your x, which is what we're doing. Going from here to there. Alright, so what if we had not chosen natural log, right? What if you chose some other log base? And probably the most other common log base chosen would be probably log base 2. So let's not use natural log, 2 letters, of course. We're using 3 letters with a subscript. We're applying log base 2 to left-hand side and then to right-hand side, not multiplying. So applying this one to the left-hand side, we are going to get log base 2 of e to the power of 3. No simplification yet. And then we're going to apply it to the right-hand side as well. So we're going to get log base 2 of 2 to the power of x. Alright. So there we have that. Pay attention to what's happening. We have all constants right there. This one is where our unknown is. It's in the exponent. So we can take that exponent and slam dunk that down in the front, because that's why we applied log to both sides in the first place, right? So we're going to get, again, exponential slammage, x times log base 2 of 2. Here, there's not much to do here. You can move the 3 down if you wish. I don't think it's super useful, but let's just do it anyway. Alright. So we get that. These are all known values. They're all constants, and then this one is simplifiable. And this is just what we're trying to solve for. So let's transform this one. Again, 2 to the power of 1 equals 2 to the power of 1 equals 2. So this whole thing becomes 1. And then we thus have we solved for x. So let's move it down here. So x is equal to the thing on the left, which is going to be 3 log base 2 of e. And then we're pretty much done with the problem. So this is answer number 2. And you might be thinking, wait a minute, it looks different from answer number 1. And yes, it does look a little different. And because there is a way to transform either answer. We could transform this one or we could transform this one, and then it's going to match up. But unfortunately, the thing we need, the tool we need in order, the algorithm we need in order to transform one answer into the other answer is something called the change of base. Alright, so let's talk about that real quick. Change of base. So if we're going back to generic log base b of argument a is equal to c. We've already learned multiple rules for this one, like 4 or 5 rules already for this. But now this is going to be the 5th or the 6th rule. I don't remember the numbers at this point, but it's not important. So here's how it works, and honestly I don't know the derivation for this one, too bad. But if you imagine there is an invisible line right there. B is the subscript, B is the base, and then A is above, right? So here's what we can do. So keep track of this. I'm going to color code this as red, color code this as blue, and then using change of base, you can change this into any log base you wish. Currently, it's log base B, but you can choose something log base. What's a good letter for the bottom base? U. Let's just put U. I don't know why. So we're changing this from log base B to log base U. Hence the name change of base rule. Since the A is above the line, then it goes above the division sign. And then since the B is below, then it goes as the argument right there. But you have to apply log base U to the top and to the bottom. So it's log base U of A, because again A is on the top of the line, so it stays on the top, and then B is the subscript, so it goes on the bottom, and then U is just something we arbitrarily chose, so U is just be some whole number that's greater than 0. Yes, U is well, it could be a fraction, I guess, right? Yeah, As long as u is greater than 0, we're good to go. I think that's the criterion that we want. We just want to make sure. For some arbitrary u value, such that u is greater than 0, we can change this thing. We can change our given problem into something like this. And it's still equal to c. Alright. So again, this little other underlying thing, I just did it for visual clarity. But again, the b is on the bottom, so it stays on bottom, and then a is on top, so it goes above the division. And you could choose any log base you wish, provided log base is greater than 0. I think this is the rule. And of course, right hand side stays the same thing. Alright, so putting that in action, just as an example, if you have log base 2 of 3, and then that is equal to, who cares what it is equal to? This one, we can apply change of base rule. So pay attention to what's on top. The 3 is the argument, and then the 2 is the subscript. Sub is below. So you can pick any log base you wish. Let's just pick log base 4, for example. Well, there's no reason, but I'm just illustrating an example. So 3 is the argument, so it stays on top, and then the 2 is a subscript, so it goes on the bottom. You have to apply log base 4, which is the chosen one, to the 3 and to the 2. And that's it. Very simple. Very simple algorithm. So I think it's surprisingly easy to remember for a lot of people. At least I think so. Most people don't have too much difficulty memorizing this one, but I think it's also very easy to forget. But did we have to pick the log base 4? No. You can be lazy like I am and just pick the log base natural log for the change of base, because it's much easier to write just only 2 letters versus 3 letters plus subscript. So if you wish, you can change it to natural log of 3 over natural log of 2. That's perfectly fine. You could also change it. Going from here, you could change it to something like natural log base, not natural log, log base 3 of 3 over log base 3. Make sure these two match up of 2. So in this situation, you could see maybe why I would choose 3, because this is argument 3, this is subscript log base 3, so we can cancel this and make it become 1. So therefore, we can transform this thing into 1 over log base 3 of 2. Which, if you notice, it's just inverted version of this one. We've swapped the place of the argument and the base. So right there, but it's underneath the fraction bar now. So that's it. That's some goofy stuff that you can do with this situation. It's kind of useful, I guess. Honestly, it doesn't show up very often in problems. Like once you learn this in your particular section, let's say it's like Algebra 2 or Pre-Calc. But now there's AP Pre-Calc nowadays. But once you learn it in your particular section, the change of base, you almost never see it ever again. But surprisingly, it does make a funny appearance in calculus. But we're not talking about calculus. Alright, so that's the change of base rule. Here it is again. It's not too bad. Here's the problem that we're doing. We got answer number 2, and then we got answer number 1. So now let's use change of base rule and just see if these two answers are indeed the same thing. So let's take this one right here. We notice that there's a log base 2 of e. This is natural log, so when we choose which log base we're going to use, well, since we're trying to see if the answers are the same, we're going to choose natural log. So here again, here's what I mean. There's an invisible line. 2 is the subscript, so 2 goes underneath. And then e is the argument above, so it stays up on top. We are deliberately choosing to change from log base 2 into natural log. But when you apply it to the top, you have to apply the same log base function to the bottom, so it's natural log of e over natural log of 2. Still a 3 in the front. Alright, and then of course that is a familiar face. It's just going to be 1. And why write it like this when you can multiply? This is technically 3 over 1, so you can multiply it to the top, thereby getting 3 over natural log of 2. Well, there it is, and of course they do match up because they are one and the same. So change of base rule allows this one to match up. So that's going in this particular direction, but did we have to change this answer? No, you could also change that answer to match it up with that one if you wish. So let's do that one as well. Well, this one, remember, that's technically log base e, so the e is on the bottom and then the 2 is on the top, right? So what we can do is we can use change of base rules on natural log of 2 on the bottom. What kind of log base are we going to choose? We're going to try to match this one. So we're going to deliberately choose log base 2. So here we go. There's a 3 on top. I'm going to keep the fraction bar right here in the middle. Again, this one, the 2 is on top, and then the invisible e is on the bottom. So we're deliberately choosing log base 2. 2 is on top. Over invisible e. So log base 2 of e. So that looks kind of gross, honestly. It's a fraction within a fraction scenario. But we still have the goofy flip trick at our disposal from our pre-algebra days. So let's simplify this a little bit more. Familiar situation, we have base 2 matching the argument of 2, so this whole thing becomes a 1. So it's 3 over 1 over log base 2 of e. So using the goofy flip trick, we can take this one, find the reciprocal, and multiply it to this 3. So this one ends up in the numerator, and this one ends up cleanly in the denominator. So we're going to get 3 times log base 2 of e. Does that match up? Of course it does. There it is. Very nice. And that's an illustration of change of base rule. We basically do it for this particular problem. We didn't have to do it, but it's just to show, it's just to verify the situation. So this route, we deliberately chose log base 2, and then this route we chose natural log as the base, but you can be kind of goofy about it. You can choose log base 10. So let us solve the same problem yet again, but now we're going to be using log base 10 instead. Why would you use log base 10? I don't know. Just in case you want to do it. So we're applying log base 10 to left hand side and to right hand side, thereby getting log base 10 of e cubed is equal to log base 10 of 2 to the power of x. So a very familiar situation, you know, because we've already done this problem twice beforehand. So same operations. You could take that 3, slam dunk it in the front, take that x, slam dunk that one in the front. We're going to get 3 times log e, and then we have x times log of 2. Again, technically base 10, base 10. Alright, here's our unknown. Here's our log base 2. Let's just divide both sides by log base 2, because that's a constant. Clear that with that. So a little bit of cleanup. We have successfully isolated the x. X is equal to what? This nastiness right there. So we have 3 times log base 10 of e over log base 10 of 2, I think. Yeah. And that's it. That's the final answer. It doesn't look terrific. It looks a little bit different from this one and from that one, but you know, we can apply the exact same rules. In fact, we can go reverse log base rule, because this is log base 10 of e over log base 10 of 2. So this is a familiar template, because isn't that the same thing? See that? See that? It says that the u here are both invisible as 10s. We have the a on top, that's the e, and we have the b on the bottom, that's the 2. So this is actually a ripe opportunity for us to use change of base. Which change of base shall we use? Well, since this 2 is on bottom, we'll put that one. So it becomes 3 times what? We're changing this whole thing. Since the e is on top, it becomes the argument, and since the 2 is on the bottom, it becomes the subscript. So it becomes log base 2 of the thing on top, e. Oh, there you go. It now matches with that one, and then that one we know can be converted into that one. So we are good to go. Yeah, good to go. Now you could be, again, you could be very goofy about it. You could use a log base of pi. Ain't nobody going to do that, though, because that's unnecessary. So pick nice ones. Most people would match bases with the base for these exponents. So people would pick natural log because it matches this one, or people would pick log base 2 because it matches this one. But honestly, it's not that big of a deal. At the end of the day, you probably have to use change of base anyway to change it to probably this form. I think this form is the one that is most preferred. It's not to say that this one is wrong, though. This one, because of older technologies, you didn't have a button that said log base x, for example. There's no way to type in a number for this base x because calculators were much simpler back in the days. So people always had to convert to base 10 or to natural log, which is why this answer was not acceptable back in the days. So if you have like an older textbook, I don't know why you would have an old textbook, but if you, for some reason, you have an old textbook, this is probably not the best answer. You would probably need to convert it into this form. Yeah. And of course, as a side note to calculus, when you have this in calculus, you want to change this using change of base to get it into the natural log form, because this is you have an algorithm for this one, but you don't have an algorithm for that one, at least not initially. Okay, that's it for the change of base and for the natural log. The natural log is not very difficult. It's just coming to terms with the symbolic representation. Just understand it's base e. That's it. It's very simple. It's very lazy. It's for lazy people like I am. Yeah. Alright, cool. Moving on. Let's actually... Wait, shall we just do problems at this point? Yeah, let's just do problems at this point. Let's start off with a few random easy ones, of course, just to keep things nice and easy. So let's say we have e to the power of x minus 5, and that is equal to something like 10 to the power of 3. So in this situation, pay attention to what's happening. We have a constant base. This is a constant base, constant exponent, but the exponent here has the unknown that we are trying to solve for. So this calls for applying log to both sides so that we can free this x from its prison, from its tower as an exponent. So the easiest one, again, I'm pretty lazy, so I'm just going to choose the 2-letter log base to apply to both sides. I'm just going to choose natural log, apply it to this side, and then apply that to that side. Thereby getting what? We have natural log of e to the power of x minus 5. Wonderful. Applied to this one as well. So natural log of 10 to the power of 3. Alright. We can do the exponential slammage down front. Exponential slammage if you wish. Now, don't write it like this. This is being sloppy. Don't ever write it like this, because then only the 5 is being multiplied to the natural log. Make sure you put the parentheticals. And then here, we're just going to do exponential slammage. Nothing to watch out for, really. There it is. So this is a constant times x minus 5, and then 3 times constant. So this one is a full constant. This is a constant. It should be a familiar one, right? So cross that out just so it becomes 1. Very nice. So we have x minus 5 is equal to 3 natural log of 10. We can therefore plus 5 to both sides. X is equal to... Wait, that's like a weird 3. So 3 times natural log of 10 plus 5. And I like this answer in particular, because I don't know, natural log just looks very clean to me, so we're done with the situation. And again, you didn't have to choose natural log base e. We can instead pick the other one. So what if you choose base 10? So we're just going to apply log base 10 to both sides, so apply it to this side and apply it to that side. I'm just going to start skipping steps. We have exponential slammage, so we're going to get x minus 5 in parentheticals times log of e. It looks like log. Alright, and then we apply the log base 10 right there. I'm just going to go ahead and do exponential slammage right away. This one becomes a log base 10 of 10. But don't forget, this is familiar. So this whole thing just becomes times 1. Alright. Cleanup time. We're going to get x minus 5. I'm going to divide this from both sides. So we have a 3 times a 1 divided by this log from both sides. Don't ever call it log, please. Log of e. There you go. And of course, just follow up by adding 5 to both sides, and then we are done with this problem. So we get 3 over log of e plus 5. So again, it looks a little different from the previous answer because now this is in terms of log base 10. And some teachers will accept this and other teachers will not. It just depends on your teacher, of course. So if you want to change this one, how do you change this one? Because in all honesty, it does look kind of gross to me. It's not my favorite answer. So since this is e, argument e, we could actually change it to natural log for the logarithm of choice when we're doing change of base. So let's just do that. Let's copy paste the 3 up on top. Copy down the fraction bar. I'm just going to extend it just a little bit. And this one, using change of base, this is again invisible base 10. The e is above and then the 10 is subscript below. So we're going to deliberately choose natural log e on top and then natural log of 10 as a subscript. There it is. Familiar face. Cancel it, becomes 1. This is a fraction within fraction situation, so we could do the old goofy flip trick. So this one multiplies to the numerator. And then the 1 ends up in the denominator, so nothing fancy there. We have 3 times log base e of 10 plus 5. And that one should match our previous answer. And we are good to go. Yes. Let's just do one more for the road, right? Let's choose something that's neither one. What if you choose a log base that's neither e or 10? Let's be goofy and pick natural log base pi. Again, nobody does this. There's no reason to do it. So we're going to apply this function to left hand side. Again, just skipping a little bit of work. We're going to get x minus 5 exponential slammage. Then we have log base pi of e. Again, looks pretty gross. Now apply the log base pi to this side. So exponential slammage rule. Log base pi of 10. There we go. This is a constant, so we shall divide it from both sides to free x minus 5. So x minus 5 is equal to that chunk divided by that chunk. So it becomes 3 times log base pi of 10 all over log base pi of e. Wonderful. So that is, in all honesty, kind of gross looking. So copy paste it. I'm going to add 5 to both sides using lazy strats. So let's plus 5 to both sides. Make sure you flip the sign. Of course. So thus we have x is equal to fraction thing plus 5. So is this satisfactory? Not quite, right? Because it looks kind of gross. But I hope you recognize this form. This thing right here is a ripe candidate for change of base because pi base for the log matches pi base for the log. So therefore, we can change it to any log function base we wish, as long as it's valid. Let's pick base e, right? So natural base 10 is on top. And then natural log of the argument in the bottom. Wait, what am I saying? I goofed up. I'm sorry, let me say that again. So this is that's in the top, and then this is in the bottom, and these two log bases are the same. So therefore, we can just kind of capture those three things following the algorithm. So it becomes log base what? Log base e, because the e is on the bottom. So natural log. And the number on top, so argument is 10. So this whole rectangular thing became natural log of 10. And there it is, clean answer. That looks much better. There's no quotient anymore. And I'm pretty happy with this particular answer. So we are good to go with that one. Alright. And of course, all our other log stuff still apply. So if you have natural log, for example, of x squared minus 9x, and let's say that is equal to natural log of what? Natural log of, let me think. 18. Yeah, let's do 18. It's pretty straightforward. So if we're doing this particular problem, you have a log function on both sides. You can see that the log has been applied to left-hand side, and then the same log has been applied to right-hand side. So we can simply negate both sides. So cancel out the log function by exponentiating, right? So that's the official step. So if you're lazy like I am, we're just going to say the argument there is equal to the argument there. So that's kind of lazy strats, okay? Yeah. I don't think this is a nice answer. So let me change the value just a little bit. Let me change the problem just a little bit. Let me think. 22. Yeah, let's do 22. Yeah, you'll see why. Okay, so again, we're just equating the argument number 1 with argument number 2. This is technically kind of sloppy. That's okay. I'm not a mathematician. So let us subtract 22 from both sides, thereby getting x squared minus 9x minus 22 is equal to 0. So classic quadratic problem, factors of 22 that sum, factors of negative 22 that summate to be negative 9. Well, 11 and 2, right? Yes. So therefore, there's an 11 here and maybe a 2 there with the x. The signs are different. The larger of the two magnitudes is negative, so the negative goes on 11x and the positive goes on the 2x. That's very nice. So therefore, we have two answers. X is equal to 0 number 1 and then 0 number 2. Alright, good to go, right? No, make sure you always double check your answers. Make sure both of them are valid. Make sure both of these answers create valid situation inside your natural log domain. Because remember, log functions have domain restrictions. So let's double check. If we take this negative 2 and we plug it in, right there we get positive 4 plus 18. So this whole argument becomes positive, and that's perfectly fine for log functions. So negative 2 is a valid answer. And of course, if we take 11, make sure that one also works. We get 11 squared, which is 121. And that is a greater magnitude than 9 times 11. Because this is literally 2 more 11s versus only 9 11s. So therefore, this will also produce a positive result inside the log function. So both answers are good, and we are happy. We're going to keep both of them. So good to go for that problem. Alright, but here is the trick to making problems more annoying for people who just want to get it done with. So this is a problem that I could have given. In fact, I did give it, right? But what we can do is we can start applying log rules to this one. So let's start splitting it just to be annoying. So problem design. We're going to split this one, factorize it into x times x minus 9 inside the natural log. And then since we have factor number 1 times factor number 2, we can expand this one using one of our log expansion rules. So it becomes natural log of x plus natural log of x minus 9. And nothing happened on the right hand side. Okay. There we go. So it's not tremendously more difficult, but here's where you can be extra annoying. So you see how this is technically base e? We could just transform this one using change of base rules. So which change of base shall we use? Let's just use base 10, because some people forget there's an invisible 10 on the bottom. So let's do that. So we have a log base 10 of x minus 9 all over log base 10 of e. Because again, remember the base e right here, base on the bottom, and then the argument goes on top. Alright. So again, it feels like I haven't done much to change the problem, but you'll see. You'll see in the end. There's the fraction, so I'm just gonna make it a little bit more annoying by multiplying log base 10 of e to both sides. So this one, for that one, we're gonna get log of natural log of x, and then this log cancels with that log for the second term. So thereby getting log base 10 of x minus 9. And of course this one distributes to right hand side as well. And we therefore get natural log of 22. Let's put the base 10 in front actually. So log base 10 of e, that's log, and then times natural log of 22. Alright, so what happens? So basically this is the problem that we have already done. I've just gone through these manipulations to change it from this problem into this new problem, and let's just look how intimidating it is. Let me shrink this real quick. Alright, that's gone. So this is the problem we are now working with. So why is it more annoying first? Well, take a quick survey. We have log base 10, we have log base e, we have log base 10, and we have log base 10, and we have natural log right there. So it seems like we have a lot of different types of logs. And the typical strategy for a lot of log problems is to simply try to merge all the logs with the same bases together. But most of the problems we've encountered before, the ones where the log bases are different, typically are simplifiable, like right off the bat, in that they have clean numbers. This is not a clean number. So what I mean by that is for prior problems, we would have had something like log base 3 of 27. You know, this is base 3, this is 27, which you can change into base 3. So at this point, this one simplifies into a 3, right? So this is what I mean by clean numbers right there. But unfortunately for the problem, this is not a clean number. This is base e. That's irrational. There's no clean way to deal with natural log of 22. So that's the whole point, right? So how do we do this problem? Well, technically we've seen how we generated this problem. So in essence, we're just going to go backwards, right? But again, take a quick survey. This one has base 10. This is base e. This is base 10, base e, base 10. So what do we do? Well, the goal is to try to get all the bases to become the same thing. It is going to be the most standard strategy. So the question is, do we wish to change all the logs to natural log, or do we wish to change all the logs to log base 10? That is the decision, right? And honestly, I don't think it matters which way you go. But let us change. You know what? Let's do it either way. Let's see if it truly is the same thing, right? Let's see. So I'm going to arbitrarily opt to make all the logs into just natural log. So this is log base 10 of e. So we're going to use change of base on that one, and then we're going to use change of base on this one, and we're going to use change of base on that one. These ones we will keep because they're already natural logs. So let's see what happens. Hopefully it's going to be nice. Again, there's an invisible 10 on the bottom and the e is on top. So therefore, we're going to get natural log of e over natural log of 10. Again, we're choosing to change all the bases into natural log. Right, so this, the first factor becomes this one. Copy paste natural log of x. This one's going to look kind of nasty, honestly. So it changes into natural log of x minus 9 over, again, invisible 10. So natural log of 10 equals what? Copy paste. No, this is not copy paste. This one we have to use change of base again. So natural log of e over, again, invisible 10. So natural log of 10. That one, we'll leave that one alone since it's already natural log. Natural log of 22. Okay. So quick peek. Well, we have term number 1, which has a fractional, which has a natural log of 10 in the denominator. Term number 2, which also has a term of natural log of 10 in the bottom. And then this is the third term, which also has natural log of 10 in the bottom. So we can simply multiply both sides by natural log of 10. So this one will cancel with this. And then this one will cancel with that one. And this one will cancel with that one as well. So cleanup step. So this one, this one you can also clean up. Remember, it's invisible e. Recognizing this form, this becomes 1. That one too, 1. Alright, so now we just have 1 times this. Very clean. And that one's still natural log. And this is just 1 times natural log of 22. Okay. Well, we have an expanded form. We have a plus thing right here. Here's a natural log. This is a natural log. So we can therefore combine these two terms by multiplying the two arguments together. We're going to get x squared minus 9x. And that's condensation rules. Keep the same log. So it's natural log. Alright. That's just like rule number 1 from back in the days. This one right here, copy paste. Wonderful. So now we have natural log of a thing and then natural log of another thing. So you can technically exponentiate both sides. You can do the fancy smancy step right there. But regardless, argument on the left hand side is equal to argument on the right hand side. So x squared minus 9x is equal to 22. So same answer as before, right? So let me just speed through this. So minus 22 from both sides. We've already done this. Factorizing this junk becomes x minus 11 times x plus 2. We have two zeros. 0 number 1, x is equal to negative 2. 0 number 2, x is equal to positive 11. We already checked this answer. We already checked both of these answers prior. So these answers are good to go. So consistent. So yeah. It's just deliberately meant to intimidate people when you have a mix of log bases, but you could just always just brute force change them all to be the same bases. And for the most part, you're going to be good. Good to go. Alright, that's it for that one. So let's start going through the problems that I've pre-written. The majority I've pre-written today. I hope they're good. But there are chances of these problems getting botched up. So problem number 1. So we have 2 to the power of x times 8 to the power of 10 is equal to natural number e to the power of 32. So again, this is in contrast to what we've been doing before, right? Typically, you can get all the bases to match up for the majority of our older problems. But now, you can't match with this e. You can get this base 8 to match with this base 2, right? By changing this one into base 2 to the power of 3. And then just use your distributive property of exponent. Just take that 10, distribute it to that exponent, thereby getting 2 to the power of 30. Copy paste right hand side. And since these two bases match up, we could just simply summate the exponents. So thereby getting 2 to the power of x plus 30 as equal to copy paste. Alright, well, again, now we reach this awkward situation. This is base 2, this is base e, but we've already done this one earlier today. So let's just take the natural log of both sides. Again, why are we taking natural log? Because we want to solve for the x in the exponent. So we need to free the x from the tower, and then we need to drop it down using exponential rules. Why did I choose natural log? Because it's only 2 letters. Okay, if you wish, you can choose log base 2 and apply that one to both sides, because if you want to match this one with this one, that's perfectly fine. But again, I'm just lazy. I want to write 2 letters only. So applying this one to the left-hand side, we are going to do the exponential slammage. So it becomes x plus 30. You know, let me not skip steps. You can skip steps if you wish. Unless you're working on a FRQ test. Then you want to show full work. Alright, so again, I'm just gonna apply full work. So we're gonna get natural log of 2 to the power of x plus 30. Left hand side, and then to the right hand side, apply the natural log to this thing, e to the power of 32. Alright. Now we can do the exponential slammage rule. Make sure you put the parenthetical, please. Times natural log of 2. As equal to, again, this exponential slammage rule. This should be a familiar friend. This is base e, argument e, so therefore this whole thing cancels and becomes just 1. Alright, well, this is a constant. This is a constant. This is still parenthetical, so let us divide both sides by natural log of 2. Divide by natural log of 2. Because we're trying to free the x. So natural log of 2 cancels from both sides. Clean up step, we get x plus 30 is equal to 32 times the 1 on top. And then natural log of 2 on the bottom. There it is, and then the final thing to do is just to subtract 30 from both sides, getting a fairly clean answer. 32 over natural log of 2 minus 30. And in my eyes, this is a very clean answer. So I'm happy with it. Alright. Again, you can choose whatever log base you wish. You could have chosen log base 2 if you really wanted to. In my opinion, it's not that much nicer, honestly. I'll show you real quick. So if we had instead went a different route, slightly different route. So let us choose log base 2, and we're applying that one to both sides. So this is the alt strat. That one I will shortcut it. This one exponential slammage. And then since this is base 2, it cancels with base 2, so thereby we only getting x plus 30 clean number on the left hand side, and then right hand side is not so clean. Again, log base 2. Oh, this is a very poopy color. E to the power of 32. There it is, and then we can solve for x by subtracting 30 from both sides, so it feels a lot faster, right? Exponential slammage, of course. So minus 30 from both sides. So technically very fast if this answer is acceptable to your teacher or to your test. So as you see, this one only required like 2 lines. But going the natural log route, you need 1, 2, 3, you need 4 lines for that one. So yeah, depends on whether or not your teacher accepts it. So personally, I like this one better because it's just natural log base e right here. Or if there's only base 10, I would also like that answer. But this one is base 2, which is, ooh, it's kind of gross. I don't like this base 2. But again, most modern calculators nowadays, modern calculators are perfectly content with having this as an input. You actually have a function button for this one on modern calculators. Yeah. I don't think phone calculators quite have this just yet. So if you're doing your math on your phone and you want to get like actual rounded answer, you'd have to use change of base on this one. So that one you'd have to do like natural log of e over natural log of 2. And then that's what you would basically input into your calculator, because your calculator on your phone can do natural logs or it can do log base 10. Yeah, so if you don't have internet reception and you're kind of in a pinch and then you have to use your phone as a last resort as a calculator, you use your phone app. No, I'm just kidding. You use change of base and then you are probably good to go. Just make sure you put parentheticals correctly and make sure you simplify stuff. The less buttons you push, the less error prone you will be, right? There's a non-zero chance that you will mess up an input. So if you minimize the amount of inputs you have to punch into your calculator, then you have a lower chance of goofing up. So same answer. Same answer as before. Yeah, so I really like this one. But either answer is acceptable, honestly. Alright. And there we have the first of the bulk problems done. And then we have another. Moving on. Alright. Moving on, we have the next problem up. It's going to be log base 9 of log. Well, that looks kind of gross. It's a log within a log function. Don't worry, it's not too bad. It's just for the intimidation factor. Is equal to 1/2. Alright, so that's the problem. Again, don't be intimidated. It's not a particularly big deal. It's just meant to look intimidating. But let's just use our log rules. So we have a log base 9 of something equals this one, right? This should be a familiar situation. So if you have log base b of a is equal to c, then you could just b to the power of c equals a. So we'll get b to the power of c is equal to a. We're going to do that. We're going to run the algorithm to that one. Okay? I think that's rule number 1 in prior streams. So 9 to the power of 1/2 equals inside the brackets. So inside the brackets is natural log x plus e to the power of 3, which is equal to 9 to the power of 1/2. Which is just square root, right? So 9 is just going to be 3 to the power of 2. We are raising that to the 1/2 power. So distributive property, 2 cancels with 1/2. Leaving with just 3. Clean. Alright, here we go. Don't forget the invisible log base e. Raise it to the 3 is equal to argument. So same strategy as the 2 previous steps, right? E to the power of 3 equals argument. So argument, copy paste that, is x plus e cubed is equal to what? E to the power of 3. Alright, so we can subtract the e cubed from both sides, thereby getting getting x is equal to 0, and then we're good to go. But, you know, always double check your answers. Is it okay if we have answer as 0? Well, 0 is the input, so it becomes 0 right here. So 0 plus not 0 gives us a positive input in our natural log. So this one will give us a positive number as well. And if you plug that into log base 9, is that a valid argument? And yes, it is. Because all logs, you need to have positive inputs, and you'll be good to go. So answer, it's good to go. Nice. Moving along, we have the fancy smancy looking problem. We have here the natural log of x minus. It should look kind of familiar because we did this maybe 2 problems ago. So natural log of 6 x to the power of 4 plus 7x cubed plus 15. Close parenthetical is equal to natural log of, kind of a funky looking thing, 1 over 33x plus 35. Wonderful. But at least, hey, all the log bases match up. Again, always do your quick surveys. We have natural log, and then we have natural log. So everything's natural log. So let's just get to condensating. So we have a subtraction here. Not my favorite thing to condensate in that fashion. So what I'm gonna do is what I'm gonna do. Let's move this to the other side. Let's move some terms around just to make things slightly easier. So we can condensate this one with this one if you really want to. But from the looks of it, I'm just gonna do a little bit of rearrangement. It's just my preference. We'll see what happens if we don't. So I'm gonna take this and add it to both sides. So plus this thing to both sides. So it's gonna end up there with a positive sign, and then we're gonna subtract this one from both sides. So it'll be minus, like so. Since this is plus, I'm just going to drop the sign. It's the only term on the right hand side now, so I'm going to drop the plus sign in front. But it's still positive. And this one I'm just going to move it closer. Okay, so I like this one a little bit better because now we have subtraction, and then this one you recognize. We can use the exponential rule by setting across the fraction bar, but we have to flip the sign of the exponent. So it becomes 3x. It becomes 33x plus 35 to the power of negative 1. Again, this is one of our exponential rules that we can use. And I'm preferring that because I don't want fractions in the end. Alright, we're just going to copy paste the entirety of right hand side. Okay, there we go. So what we can do is we do the exponential slammage. So this one, slam it down in the front, so the coefficient becomes positive 1, and now it's easy. It's easier. Well, it wasn't that difficult before, I guess, but it's cleaner to condensate this one. So we're just going to multiply the two arguments. So argument number 1 times argument number 2, thereby getting 33x squared plus 35x. Clean, and then this one is just copy paste. Yeah, technology. Alright, we have another situation we've seen before again. This is why I mentioned it earlier. We have natural log function applied to the left hand side, and then a natural log function applied to the right hand side. We can therefore equate the two arguments together, but if you wish to show official steps, just exponentiate both sides with base e. And then this one will cancel with that one because they're inverses. This one is inverse of that one. So therefore, argument number 1 is equal to argument number 2. So let's move this, or let's copy paste. I said copy paste, but here I am just writing it out. Whoop. It's okay. There is some niceness in just writing these things out. There we go. So this is what? Can we cancel anything from both sides? Not that I'm aware of, so we have no choice but to move it over to one side. So we're going to subtract this from both sides. We're going to get 6x power 4 plus 7x power 3, and then minus, I'm putting this in order, descending order, minus 33x squared. This is the next one, so minus 35x. That's it, and then plus 15. And since we subtracted this on both sides, that becomes a 0. But I'll put it right here. And this should feel familiar. It's going to be our old enemy from back in the days. It's a polynomial function. It's equated to 0. So take your favorite thing to do. What's your factoring algorithm for this problem? This is degree 4 polynomial, so we can have up to 4 real solutions. Well, it's not obvious if we could factor by grouping, right? You'd have to manipulate this middle term here, and I'm not particularly fond of working with this one. So let us use standard algorithm rather than trying to force special cases which may or may not work. All right. But let's double check. So we're going to resort to synthetic division. We have 4, 3, 2, 1, 0. So all terms are present and accounted for. Let's just extract them now. So 6, 7, negative 33, negative 35, and 15. Prepping for synthetic work division. Synthetic division work. And factors of 15, 1, 3, 5, and 15. Factors of 6, 1, 2, 3, and 6. Alright, so those are all our possible candidates, plus or minus, of course. Quick survey of the signage changes. We have plus to plus, we have plus to minus. That's one change, that's two changes. We have two changes, so according to Descartes' rule, we can have up to two real positive solutions or 0, so not super useful. Let's check the other one. So if we do a negative number input, what happens to the sign changes? We are going to get plus to minus, minus, plus, plus. So we get 3, I think that was what, 3 sign changes? Let me double check. 1, 2. Oh no, we also get 2 sign changes. Okay, so not tremendously useful, unfortunately. So Descartes' rule of signs wasn't super useful. So any number is as good as any number to start off, except 15. Don't ever start with 15. Let's pick 1. It's fairly neutral. Drop the 6. Product. Sum. Product. Sum. Product. That's not looking good. So minus 55. And then product, negative 55. Sum, we get negative 40. Yikes. So 1 has failed, right? So why did 1 fail? Well, this is too large of a magnitude, so this magnitude needs to be smaller. So this one needs to be smaller or positive, right? Yeah, it needs to be positive, which means this one is too small, which means this one is... I don't like the way this is going. Okay, wait. Let's just pick a different numbers. Let's record this for posterity, of course. So 1 as a 0 candidate did not give us a 0, so therefore this is not a 0. But let's keep track of this. So 1 got us a remainder that's negative. Negative remainder. Okay. You know what? Let me keep this. Just in case. Because I feel like sometimes I just really botch up the mathematics. Alright, let's pick something a little bigger. Let's pick 3, for example. Alright, let's see what happens for that situation. Again, copy-pasting the coefficients, following standard algorithm for synthetic division. Yeah, it's kind of cluttered. So picking 3, right? 6, and then 18. That looks like it's too large already. 25. That's not looking good. So that's too large. The numbers are snowballing too much. You see that? Let's just see what happens anyway. It may be of something of interest. So 3 times 25, 75. Summate that one is 42. Yeah. 126. And then that's 91? Yeah, 91. Yeah, 91. And then lastly, that's going to be a big positive number, and this is also a big positive number. So that's kind of informative, right? So when we test 1 as a 0 candidate, we got a negative remainder. We test 1. We test 3 as a 0 candidate right here. We got a positive remainder. So neither of them are zeros, but according to intermediate value theorem, between 1 and 3, there should lie a 0 between those two. So which of those combos produces a number that's between 1 and 3? 3 over 2? 5 over 2? So this is one possible candidate that is between 1 and 3, and then 5 over 2 and 5 over 3, right? Knowing my brain, I'll probably pick this one. Yeah. Let's try 3 halves. That should work out. So again, according to intermediate value theorem, there should be a 0 between 1 and 3. I'm picking 3 halves as a candidate, and we'll see where that one goes with the algorithm. Copy paste. Copy paste. Negative 35. And positive 15. Alright, here we go. Drop the 6. Product is 3 times 3, which is 9. Summates, which is 16. 8 times 3 is 24. And summating that one is 9. Negative 9. Wait, what? That does not look right. Mission failed already? Well, let me think. Yeah, this is an odd number. That's bad. Well, you see there's a 3 here and there's a 4 here. That gives us an odd, which is not divisible by 2 nicely. Negative 9. It is what it is, but let us finish off. Maybe we'll narrow our goalpost for the intermediate value theorem. So multiplying those two, we're going to get a disgusting negative 27 over 2. That one gets us an even bigger negative. What is that? This is approximately... Well, actually, no, we could get that exactly, right? Negative 27 over 2 is negative 13.5. Yeah. And summating those ones, we're going to get negative 48.5. And then product is approximately negative 24. No, I'm sorry. This one divided by 2 first is negative 24.25, and then times 3 gets us a big negative, I'll say. And then this gets us a negative remainder in the end. Again, suboptimal, but hey, gives us a little bit more of a shrunken range for intermediate value theorem. So, according to intermediate value theorem, there should be a 0 between 3 and 3 halves. So, we're guaranteed a 0 between those two values unless I botched up the mathematics somewhere along the way, which is likely. Okay, so this one we've just tested that one. I thought that one would have worked, honestly, but it has failed. So which of those answers is between 3 halves and 3? I think it's 5 over 3, right? Unless my mind betrays me again. Let's see. I think that's between... Well, let me see. Is this one greater than 3 halves? Can't believe I'm doing this. 9 in comparison to 10. Yeah, 10 is greater. Okay, so we're good. We're good. Yes, so 5/3. This had better work, honestly. If it doesn't work, then I'm sorry. I failed. So we're testing 5/3 as a 0. Standard procedures. Yeah. Well, at least it's divisible. 2 times 5 is 10. Oh no, it doesn't work. Because this is 17, and 17 is not divisible by 3. Oh no, don't tell me I messed up the math somewhere. That's going to be the worst. Okay, well. Shall I carry on with this? Well, 6 times... Oh my goodness, this is really annoying. It's less than 6, so it's less than positive 30. So it's less than positive 30. So let's just say it's like negative 3. Again, I know this doesn't work, but I'm just rounding off my numbers to make the operation nice. It's a negative thingy, and then this is like a negative 40-ish. And then, yeah, that's like what? Negative... A big negative, size negative in comparison to 15, so the response is negative. Okay. That is again very, very unfortunate. Which means we've narrowed it down just a little bit more for the intermediate value theorem. So we have a valid 0 between 3 5/3 and positive 3. All right. So the question is, what is between those two? Is it 5/2? It was 5/2, right? It's got to be. Yeah, okay, maybe it's 5/2 after all. That's the one I avoided. It better work. We love long division, don't we? Synthetic division. No, I'm just stealing the numbers. Okay, I have confidence this will work. It better work. 3 times 5 is 15. And then summating that is 22. Good. It's still divisible. So we have 11 times 5, which is 55. Good. That's going to be 22. Perfect. That is 55. Nice. And then summating that is positive 20. It's positive? Oh, woe is me. Right, well, it's 20 and then 10, 50. What? Well, it's positive. Interesting yet again. There's a chance I may have miscopied the problem, right? We have multiple considerations. We have multiple hypotheses at this point about where things could have possibly gone wrong. So this is very strange. So I must have missed the math somewhere. Okay, so for the sake of efficiency, let me just cheat and go on my calculator real quick. What is supposed to be the 0? Because I probably botched up the synthetic division somewhere along the way. Yeah. Positive 1/3 should have worked. Interesting. Positive 1/3. That means I must have really screwed up one of these. Okay, well, I did the work, and unfortunately, it did not work. So, interesting. I'm going to have to check these numbers afterwards. But, long story short, let's pretend none of that ever happened. So we have this particular polynomial. It is equal to 0. And here is the correct one, 1/3, according to what I've written before. So 1/3 needs to work for this problem. Interesting. Okay. Oh, I think I know. This is technically correct. Okay, I'll talk about that later. Alright. That's fine. Let's look at this one. So we have 1/3. And then, what do we have? 6, 7, negative 33, and then negative 35, and then 15. Alright, so dropping that, product is 2, summation is 9, product is 3, summation is negative 30, product is negative 10, summation is negative 45, and then that's what's supposed to happen if I'd chosen this candidate correctly. Remainder 0, which means this is a 0 of our function, which means this is the quotient. Alright, so let's transform that from 0 into a factor. So it's x minus 1/3, which means these ones are exponent 3. So 6. We could factor 3 from each of these. Let's do that first. So divide by 3, divide by 3, divide by 3, divide by 3. So factoring out the 3, we are going to get divided by 3 is 2x cubed. And then divided by 3 is 3x squared. Divided by 3 is negative 10x. And then divided by 3 is negative 15. And again, we chose to divide by 3 so we could transfer to this one, distribute it, and make it look beautiful. There it is. And this one, we can continue to do synthetic division on that. So let us extract all the coefficients. This is 3, 2, 1, 0. Sounds good. So for the sake of efficiency, I'm just going to cheat. Negative 2/3 is the correct 0. So let's pretend we got really lucky. Okay. Alright. Dropping this down is a 2. Multiplying that is negative 3. Summating is 0. Product is 0. Summation is negative 10. Product is positive 15. Summation is 0. Perfect. Of course, that's how I made the problem, right? So that means since this one produced a 0 remainder, then this must be the other factor. So x minus minus, which is plus 3/2. This one. What is that, right? So we've gone from exponent 4 to exponent 3. We divided out one more x power 1. So this is x squared. It's a quadratic at that point, yeah. So we have we'll divide by 2, yes. So dividing by 2, we're going to get 1x squared. And then divide by 2, we get negative 5. Alright. Don't forget about this particular factor. You got to copy paste that. Okay. So we can beautify this answer by distributing the 2 to each of those terms. So on cleanup, we're going to get 3x minus 1 times 2x plus 3 times x squared minus 5. And then this is where I'm going to point out the situation, okay? So we have these clean answers right here. We have a real solution here, we have a real solution here, and if you notice that, that's a difference of 2 squares, right? I should have put a plus 5, but I didn't. Okay, so the reason why I'm mentioning this is because technically this has 2 real solutions. They're just irrational. So if we set x squared minus 5 is equal to 0, we plus 5 to both sides. Getting that, and then we can take the square root, apply the square root to both sides. And that's going to result in x is equal to, don't forget plus or minus, because we're going from even to odd exponent. So plus or minus square root of 5. So those are our other 2 solutions, which agrees with the Descartes rule of sign, because one real solution is positive 1/3, and then with the other one is positive root 5. So those are our 2 positive real solutions right there. And of course we have 2 negative real solutions as well. So 2 negative real solutions is negative 2/3 and negative root 5. Did I say 2/3? I mean 3/2. Yeah. Okay, so those are our 4 real solutions. So that's why the intermediate value theorem was kind of leading nowhere useful, because the candidates we are choosing are only rational, and they're from right here. So you can see that there's a narrowing of sorts. We narrowed it to somewhere between 5/2 and 5/3, right? And if you evaluate what square root of 5 is, that's just like a little over 2. Square root of 4 is 2, so square root of 5 is close to 2, right? So if we slam dunk that into the calculator, we get this one is approximately 2.23, which lies between this positive candidate and this other positive candidate, which producing, intermediate value theorem guarantees this answer between those 2, and that's why it seemed kind of boggling, because the actual 0 was irrational, and using synthetic division wasn't going to pinpoint that, unfortunately. Yeah, so this is all in vain, unfortunately. So you just hope that whoever is designing the problem for you, that they give you reasonable situations. So this would be a bad problem to give to someone, in my opinion, because of this existence. Having a plus here is actually okay. So if the problem maker, and I was the problem maker, if this had been x squared plus 5, then this would be a good problem to do, because this one would not lead you astray when you're attempting to use intermediate value theorem. Because, when you're a problem maker, you want to give reasonable situations to whoever's doing your problem. You don't want to make something that's like extra annoying. So this is technically a bad problem. Poorly written. I mean, it's a problem that is solvable, but it is kind of poorly designed. Yes. But there we go. So let's not get lost in the sauce. Well, so what exactly happened? Well, we have 4 real solutions, but what are we doing again? Well, this is what we're doing right here. So therefore, let's just take this one right here. So 4 real solutions. Some of them are more irrational than others, of course. Let's take that and let's consider which of those are valid responses. Which ones are valid within the domain of our natural logs, right? Okay, so right off the bat, this is easily allows us to eliminate 2 of our answer choices because log domains only take in positive inputs. Then this one is not a valid solution, nor is this one. So these are probably the only valid solutions, I think. So if you plug in 1/3, then this will be positive, and this whole thing is positive. That's fine. If you plug in 1/3, this whole thing becomes positive, so that's also okay. And that's also okay. So 1/3 is a valid answer, and I think the same is true for this one. Yeah. So in terms of answer choices, we have 2 real solutions for this particular problem. So it's the irrational one and this fractional one, which is this is unintended, but it works out. All right. I absolutely love it when problems goof up like that. But moving on to next problem, of course. We have natural log of the cubic roots of, so function within a function, we have e to the power of 8 times x, and that is equal to 3. Why is this so extended? Alright, so that is our problem. This is log of this thing right here, but remember it's base e, we could just simply exponentiate situation, right? So we shall, or you could technically do this, is the official work. So this one will cancel with that one because they're inverses, and we're left with e to the power of 3 on the right hand side. So let's copy paste the argument. So cubic root of e to the power of 8 times x, that should be equal to e cubed. Alright. And of course, since this is a cubic root, we can undo cubic roots by raising both sides to the power of 3. Since this is 1/3 exponent, we can raise it to the 3, thereby negating it. So cubic root is inverse of cubed exponent. So this one undoes that one. But we got to cube this side as well. And no plus minus shenanigans, because this is going from cubic. Eliminating by using a cubic. Alright, so we're going to get e to the power of 8 times x, and then that is equal to, distributive property is 3 times 3, which is 9. Very good. We can divide both sides by e to the power of 8, thereby getting e power 1. So final cleanup, x is equal to e, and we are good to go. Very nice problem. Of course, I made the problem. And I say this right after the disaster of the previous problem, right? It's okay, you gotta take your victories where no one else will give them. Alright, next we have kind of a random problem. It doesn't look like anything pertinent to what we really covered today, but that's okay. It's kind of a mix-up, right? So we have log of 100 to the power of x plus 4. And as good form, I should probably put it in parentheses, but I don't think I need to do that. But I'm going to do it anyway. Alright. Is equal to 3x. Wait a minute, this does not look like a correct... Oh, wait, it's okay. Okay, so that's a particular problem, but don't forget, if you have log with no indicated number on the bottom, there is always an invisible 10. There it is. Alright, so 10 to the power of that equals the argument. So again, 10 to the power of that is 10 to the power of 3x, should give us the argument. Nothing fancy here. This is base 10, this is base 100, this is base 10. We can match this base with that base. So this is a standard problem. So 10 to the power of 2. We've successfully matched those two bases. Copy paste the exponent. So yeah, that's just 100. Copy paste that. Use distributive property of exponent. And then drop the base. So I'm just going to go ahead and drop the base right here. But I'll be sure to use distributive property on that one. So we're going to get 2x plus 8. And again, we drop the base is equal to 3x. Okay, so not even a hidden quadratic. We're going to subtract 2x from both sides, getting x is equal to positive 8. And then we're done with this problem. Quick check, spot check. Yeah, it's okay. Everything falls within domain, so we are good to go for this particular problem. Alright. Now we have a natural log. This is what at least we've emphasized more today. So we have a natural log of 1 minus 3x. Okay. That is equal to 2 times natural log of x plus 3. Wonderful. Nothing too fancy, of course. We have a log base, a natural log here, which matches with that natural log, so there's not too much to be done. We do have this funky coefficient in front, so we can't just willy-nilly drop the natural log from both sides. So this is the wrong step, okay? So don't do this. That is an illegal move, because you can only drop the logs if the log is the outermost function being applied to the whole situation. So this one is applied to this argument, and then that one is applied to that argument, but the 2 is applied after the log function, so you can't just willy-nilly get rid of the natural log in that particular fashion. It's akin to doing something like this, okay, just to show you as an example. If you have 10 squared is equal to something like 2 times x squared. So this one situation, you can't just cancel this squared with this squared because you're ignoring this 2 in the front. Okay, but that's not what we're doing. This is just a similar situation. So what we can do is we can take we can take this coefficient 2 and slam dunk it, reverse slam dunk it back to the top. And that'll allow us to cancel the log function from both sides. But let us first rewrite that one. So again, reverse exponential slammage takes us to natural log of x plus 3 squared. Like that. Okay, no one puts it in brackets. Oh, that looks unnecessarily convoluted, but that's okay. So now you can cancel the natural log from both sides by doing this junk. That's the official step again. But this is the inverse of that one. This, well, let me clarify just a little bit. This is just 2.72, etc., right? But the fact that we're taking this one and putting this as an exponent for this one is the inverse of natural log. So that's why they cancel out. Copy paste. Same thing here. Again, exponentiating. The fact that this one is raised to this power, they will undo each other in that fashion. Copy paste this. Alright, so we're going to end up with a quadratic is equal to this thing, which means this whole thing just becomes a quadratic problem. Make sure you distribute this properly. This is the wrong answer, of course. It's not proper binomial expansion. So let's follow proper algorithm. So square that first. So yes, we do get this one. This one times this one times 2 is the algorithm. So it's plus 6x, and then last one, yes, we do square the positive 3 as well. So don't forget that middle term. Alright, we're going to basically add this to both sides, and we're subtract 1 from both sides. So therefore, 0 is equal to x squared plus 9x. What is that? Plus 8? Yeah, plus 8. Okay. And of course, this is a quadratic. Is it factorizable? Yes. We have x plus 8 and then x minus plus 1. Yeah. Both signs are the same and both signs are positive. So positive 8x plus positive 1x does give us 9x. And then of course, positive 8 times this one gives us 8. So two solutions. As candidates, we have x is equal to -1 and then -8. And you notice I said candidates. Don't be satisfied with this one. You should backplug these answers to verify that they are in fact part of the domain. So let's take that one. If we plug the -8 in here, this becomes a big positive-ish. That's fine. But if you put -8 in here, it becomes an argument that's overall negative, and that one we cannot have that situation. It breaks our log functions. So this is not a valid answer. That will be extraneous solution. So -1, plug it in. Yep, it changes to positive. That's fine. Plug it in there. It's also positive. So -1 is the only valid solution. So no -8. Sorry. Only this one. I think that's it for this problem. Let me make sure I didn't botch something up real quick. Plus 3 to both sides, yes. -1 for both sides, yes. Okay, I think that's correct. Good to go. Alright, next up we have this goofy looking problem. And it's just to throw people off. It's not exceedingly difficult though. So we have e to the power of e to the power of x minus 3. It just looks funny. But don't be intimidated. What is that equal to? That is equal to positive 3. Alright, so kind of awkward. We have an exponent with an exponent. But where is the letter we're trying to solve for? It's part of this exponent, which is trapped in this exponent for this base. So this is what we need to free first from this thing as an exponent. So therefore, we're just going to apply the natural log to both sides. Again, I just like natural log a lot because it's number 1, it matches this one, and number 2, it only has 2 letters. So applying it to this one, we're going to show full work. We're going to get natural log of e to the power of that chunk. And applying the natural log to right hand side as well. Yeah, we'll take that in exponential slammage. Yes. Yes, indeed. Times this thing right here. Recognize that junk. This one just cancels and becomes 1. And now we have a cleaner situation. We have e to the power of x minus 3 is equal to natural log of 3. Well, exponent still has the letter of interest. This is a constant. This is a constant. Don't think about this as a variable. It's not a variable. Because natural log of 3 is just a clean, irrational number. But it's just a constant. So we need to free this from the exponent, so we do another to apply log to both sides. So applying it to the left hand side, that looks good, but you apply it to the right hand side, it looks kind of weird. We have natural log of 3. That's okay though. It's just a number. Alright, we can do exponential slammage. And that's a familiar face. Yeah, that just looks absurd. But anyway, this one cancels. And it becomes 1. That's nice. X plus 3. X minus 3, I mean. Copy paste. Okay, we're just going to add 3 to both sides, and we'll get our answer, and we'll be done. So it becomes 3 plus the funky natural log of 3. Not the most, not the nicest looking answer, but it is an answer, and there aren't any violations that I can see. So we are done with this particular problem. Domain check? No, we don't need to do domain check because exponentials can take any inputs, so we should be good. So this, again, just looks kind of funny, but it is a valid answer. Alright, good to go. Exponential with an exponent is good to go. Moving on, of course. Now we have this particular problem. We have natural log of x is equal to log of x. And this is kind of a funny looking problem, but I say that a lot, don't I? It is kind of funny because we have natural log here and then we have log there. So unfortunately, we can't just cross cancel the logs from both sides. There's no valid thing to do that. So if you exponentiate by putting e as the base and these are the exponents for those e's, that ain't gonna, well, this one could cancel out. So we'll get x is equal to e to the power of log x, which we don't have anything nice to deal with this because this is base e and this is base 10. So not the nicest situation. So exponentiating, again, we cannot cancel this one with that one and get x is equal to x, unfortunately. So what can we do? Well, we can, again, this one is mismatched, so we cannot move them to one side to combine them directly. So the only thing we have left to do is we can resort to doing change of base rule. And the decision comes down to whether or not, like, which log base do you want to use. My preference is for natural log, so I'm going to transform this one. So I'm going to copy paste the left hand side. It's going to be natural log of x is equal to this one right here. X is the argument. There is invisible base 10. The 10 is a subscript, so it goes below, and the x is above. I'm going to change them all to match up with this log base. So log base n, natural log of number on top, the argument, and then over natural log of subscript number 10. Alright, so some moves are better than other moves. Don't start canceling things from both sides at the moment. I'm going to move everything over to one side. So let me move this one to left hand side by subtracting it from both sides. So we're going to get natural log of x minus this thing from both sides. Natural log of x over natural log of 10 is equal to, again, we subtract this from both sides, so we have 0. The reason why we want to set this up is because we have times, we have multiplication to terms is equal to 0, so we could just use zero product property. But this looks kind of funny if you're not used to dealing with this. It might not be obvious what to do. But this problem right here is very similar to x, something like this. It's like x is like 2x minus x over 10. This is a very similar situation. In fact, I would categorize it as the same scenario. So if you were dealing with something like this, how do you solve for x, right? This is just a factoring situation. We're going to slap on the old parentheses and factor out the x from those two terms. So we get x is 2 minus 1 over 10 is equal to 0. And then you can do what? Simplify this junk. X times, what's that, 20 minus 1 is 19. And you isolate the x that you care about, and then you multiply 10 over 19 to both sides, you get 0, and then we're done with the answer. So I'm trying to tell you that this is pretty much the analogous to what we currently have, which is right here. So the unknown is here and the unknown is there, so we can slap on the old parentheses and factor out the natural log of x from both terms, thereby getting natural log of x times 1 minus 1 over natural log of 10. Okay, so technically we have factor number 1, which has our letter of interest, and then this one is just a constant, because that one doesn't have a letter of interest, and then this one, neither does this one have a letter of interest. So this whole thing is just a constant. So it is safe to divide both sides by the entirety of that junk. Again, it's just a constant. We shall divide it from both sides. And that allows us to cancel this one. 0 divided by this chunk is still going to be 0. So on cleanup step, we get natural log of x is equal to 0. So again, this is just a constant. You can divide 0 by a constant as long as it's not 0. And this is definitely not 0, okay? Because this is 1 minus, is this 1? No, it's not. Because this bottom thing is going to be a rational number. You could slam dunk it in your calculator if you wish. But this is not going to be 1. So this whole thing is not 0. So you could divide both sides by the parenthetical. Alright. Now that we're at this particular stage, it's base e to the power of 0 equals x. Of course, anything to the power of 0 is just going to be 1. X is therefore equal to 1. And we're good to go. But make sure you back plug to check in. So can we plug in 1 here? Yes. Can we plug in 1 there? Yep. The answer is good to go. So that was a change of base problem right there. Next problem up, we have multiple log types. We have log base 3 of 4x plus 5. We have equals and then log base 2 of 32. Well, that one is resolvable right off the bat. And then we have log base 3 of x. Alright, so again, most of these logs are matching, but there are 2 of them. There's log base 3, log base 3. So that's probably going to be the bulk of the problem. We have log base 2, but it's of a constant 32, and this one is a workable situation. Because we know 32 is just going to be 2 to the power of 5. Yeah, 8 times 4 is 2 times 2. Yeah, 2 to the power of 5. Yes. Alright, so let's just resolve this situation first because it's unnecessarily verbose. So we have log base 2 of 2 to the power of 5. Exponential slammage. Thereby the whole thing becomes just 5. Copy paste that. And then copy paste that. Alright. So we have log base 3 on one side, we have log base 3 on the other side. So usual strat is to move and try to consolidate all matching log bases to one side. A very generic strat, but it's effective the vast majority of the times. Okay, so we have a plus log base 3 of x is equal to 5. So again, we just added this to both sides, and because this log base matches this log base, we can use condensation rules, multiply this argument with that argument inside the log base 3. Here we go. We're going to get 4x squared plus 5x. That's nice. And then now we can just exponentiate. We can put 3 as the base for this exponent number 1. And this will be exponent number 2. So this one will basically negate that one. This one is, we'll leave it alone. So we have 4x squared plus 5x is equal to, no, this one, just kidding, we're not going to leave it alone. Ooh, did I mess up this problem? I think I did. I think I meant to do 125, but now it's not 125. Wonderful, right? Okay, well, let's just try to do it as best as we can. 3 to the power of 5. What is that? That's 9 times 9 times 3. That one is 27 times almost 10, so that'll be 270, but we don't have that many. We only have 1. We have only 9. Wait. We only have 9 27s, so we have to take away 127. I think I messed up the problem already, but that's okay. It's still doable. Alright, so we have 243. I hope that's correct. Yo, you know what? This is overly complicated. This is just 81 times 3. That's clearly 24 and a 3. Yeah, okay, that's much simpler. Let's move it over to the other side, of course. I really hope this problem is resolvable, please. Alright. Factors of 4. That's going to... Yeah, I think I messed up the problem. But I think it's still answerable if we use quadratic equation. So let us use quadratic equation. It's going to be negative b. I know it's going to work because this is a negative number. And this is like... Yeah, this is a negative number. So we'll get a positive inside the discriminant test. Inside this thing right here. It's going to end up being positive. So it will be plus or minus. Yes. Plus or minus b squared. Minus minus. Right? So minus 4 times a times the c value. You will see that the negative signs will produce positive all over 2a. So x is equal to that whole nonsense. Okay. Well, I don't want to fuss over this too much. That's going to be our answer, but make sure you check for extraneous solutions. So I will input this into the calculator because honestly, it's kind of annoying to deal with. So let me just resolve the square root portion first. So we have 25 plus 16 times 243. That gives us an irrational 62.55-ish. Copy paste the rest of that junk. So it's 5 plus or minus that all over 8. Alright. So let me get the first positive answer. I think the negative answer ain't gonna work. So this one is approximately 7.19. And just for completion's sake, I'm just gonna go get the other negative answer as well. But again, it's probably not gonna work. So now we have the negative 62.55. Then minus 5, and then divided by 8, which gives us negative 8-ish. So negative 8.44. That's our two x candidates for zeros. So we'll take these two numbers, copy them, and go back to the original problem right here. Yeah, you're going to see that the negative answer, as I said before, it ain't going to work because it falls out of domain. So this is not within domain of this particular function. So that is not a valid answer. But this one is valid. We can plug it in, yes. And then we can plug that in, yes. So this answer is good to go. Okay, not a nice answer, but it is a valid answer. So again, I don't think I had meant this. I think I had meant to produce a 125. It seems like I messed that up a lot. I keep thinking like 3 to the power of 5 is 125. But it's not. It's 5 to the power of 3, so I must have flipped it in my brain. Yeah. Well, at least it still worked out in the end, so this is our only valid solution. Not this one. Okay. Still workable, though. Next problem up. We have e to the power of x minus 3. Is equal to cubic root of 25. This seems much easier. I think we've regressed in difficulty, but that's okay. Take a quick survey. Of course, we have a constant on the right hand side. We have constant base with a letter trapped in the exponent. So let us simply apply log to both sides. Natural log. Applying to this side, we know that this one will negate that one, and this one exponential slammage. It's just going to give us x minus 3. We got to apply natural log to that side as well. Alright, and then we simply just add 3 to both sides. So x is equal to, successfully isolated, and plus 3, so 3 plus the rest of this chunk. And we're good to go. That is a valid answer. Is it a nice looking answer? No. But if you want to, you can transform this into a fractional exponent. So this part right here, you can rewrite it if you wish to 5 to the power of 1/3. So when you have this, you could do the exponential slammage right there, if you really want to, but I don't think it's that important. But if you want, slammage. You get this as the final answer. I guess it looks a little nicer than this fraction, than this radical right there. But it's not that much better, but this is a valid answer. As is that one. So again, random difficulty change right there. Alright, next problem up. We have natural log of 2 is equal to natural log of 4. That's already matching up and looking good. But kind of awkwardly, times natural log base 5 of 6th root of 25x. And that's the problem. Okay, so a little weird because, let me make sure I copy this problem correctly. Yeah. Okay, so we have a natural log here, we have a natural log there, but this is a natural, this is a base, log base 5. So mismatched. So what we can do is we can at least get those two together. Let's divide natural log of 4 from both sides. So divide by natural log of 4, divide by natural log of 4. We're doing that because we want to consolidate the natural logs together. Because now, if you recognize this, this is a prime candidate for change of base rule. So hence this division move. So cancel this from right hand side, and then this one we can transform it. Remember the rule, it's the number on top is the argument, and this is, since it's on the bottom, it becomes the subscript. So natural log of 4 of 2. Again, subscript. Alright, and then we copy paste the right hand side. 6th root of 25x. This one. Hope you recognize that one as well. Well, you could ask yourself, you could do the sub problem if you don't see it right away. That's okay. We have log base 4 of 2 is equal to some number. And that number, once we figure it out, we can replace the entirety of this one with that number. So 4 to the power of what gives us 2. So if you want to do the long step, this one just becomes base 2 to the power of 2 in the parenthetical. This is exponent 1, so we can change this one, distributive property of exponent, so it becomes 2 to the power of 2n is equal to 2 to the power of 1. You drop the base since they're the same, and therefore we have 2n is equal to 1, and thus n is equal to 1/2. Again, if you didn't see it right away, with this one we can transform it into 1/2. Copy paste. This one I'm going to be lazy. There we go. Alright. Is this a nice situation? I hope this problem works out. It's doable. It just might not look very... Oh, it's doable. Never mind. So this one we could exponentiate. We can use it as base 5 to this exponent is equal to base 5 with that as an exponent. So this one will cancel out that one. So that's one official strat. Or you can just take this one, raise it to the power of 1/2 equals the argument. They lead to the same conclusion. So let's do it that way. So again, base 5 to the power of this one equals the argument of the log, which is the cubic, not cubic, the 6th root, 25x. Alright, well, we can transform it from radical notation into exponential notation, which is always more informative. There it is. Again, we're changing the radical notation into fractional notation, covered in a different stream. Okay. So unfortunately, the bases don't quite match up. They look like they will match up though, because this is going to be base 5. This is also base 5 potentially. But the exponents are kind of gross. So what we can do is we can raise both sides to the power of 6 if you want to do it. But just be aware that if you raise both sides to the power of 6, there can be some potential domain issues. Because if you raise both sides to the power of 6, you will get rid of negative signs as a warning. But I don't think either of these terms will be negative. So let's just raise both sides to the power of 6. So 6 distributive property of exponent. 6 over 2. 6 times 1/2 is going to be 3. And then of course this one negates. Alright. That's what we get. And 25. That's just 5 squared, right? So we can divide both sides by 5 squared. Divide by 5 squared. Cancel, cancel. And then of course, exponential rule, same basis, just subtract the exponents. X is therefore equal to 5 to the power of 1. And I think we are good to go with this problem. Thankfully it worked out. I was a little worried that it wasn't going to work out from this part. But it works out. Wonderful. Domain check, of course. Yeah, it works. No domain issues. So we are good to go with this particular problem. Alright, let me take some, refill my tea real quick. So mostly the same type of problems. Just a few potential tricky things to watch out for. Invisible notation, invisible numbers, and the now newish change of base rule. But nothing too revolutionary. Okay. We have the next problem up. We have log base 2 of x minus 1. And that is equal to log base 2. Good, the log bases are matching up. Log base 2 of e, that's ugly looking. And then now we have mismatched log base, log natural log of 30. And lastly, minus log base 2 of x. So it seems that most of these are going towards the direction of having log base 2, right? Here's a log base 2, there's a log base 2. We should probably get this one to the other side to combine with that term. And then this thing is not as good. Yeah. Okay, so let us simply add log base 2 of x to both sides. So plus log base 2 of x. I don't know why I'm showing my work for this one. Sometimes I feel like it, and sometimes I don't. Okay, so for visual clarity, step clarity, I mean, let's add log base 2 of x to both sides. So these two will thus cancel, and then those ones are combinable. I'm not going to skip the step here. You can skip step. You can skip this condensation step if you wish. You can just simply consolidate them right away, if you're comfortable with that. But I'm going to show full work. This one is left over as gross. Yeah, well, that's that. So let's use condensation rule. This is addition between log base 2 and a log base 2 term. So therefore, just multiply the two arguments together, thereby yielding x squared plus x. Minus x as the combined argument inside log base 2. Again, just condensation rules. And this other side doesn't look as nice. Copy paste. Alright, let's take a step back. Again, it looks like the problems want to go into the direction of having log base 2. But let me think. Well, we want to get the log bases to match up, so we can force log base 2 into this situation. I actually don't think it's the best idea, though. So, rather than that, rather than doing that, changing everything to log base 2, I'm just going to move log base 2 from this side to that side because there's an opportunity for change of base. So that's what I'm going to propose. So let us divide log base 2 of e from both sides, because again, we're trying to get this one with this one for the change of base setup. Learn to recognize your setups. So this one cancels with that one. Alright, and of course this one is log base 2, log base 2. The argument on top is x squared minus x. The bottom argument is e. So therefore, we can actually change this into natural log to match with that one. So natural log base e of that argument. So here we go. Natural log, which is again base e of this one. So change of base rules. This is going in reverse and then equating it with natural log of 30. Alright, I think that's an optimal situation. We have natural log and natural log. Therefore, the arguments, we can equate them together using this particular formal step. So cancel, 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 cancel. So therefore, x squared minus x. We're going to subtract 30 from both sides is equal to 0. Hey, it's our classic quadratic problem coming back. Factors of negative 30 that's summing to be negative 1. That's a negative 6 and a positive 5 inside these factors. So therefore, two solutions, x is equal to negative 5, which is probably wrong, extraneous, and then positive 6. But always double check. Don't just auto assume. Okay, so we have two answer candidates. So you see that the negative 5 will produce a negative argument. This is the easier one to check, of course. Negative 5 is an invalid argument. So this is extraneous, as we've concluded. And then the positive 6 should work out. Yes and yes. Okay, so this answer is good. Clear that. Moving on. We have natural log of a quotient. So e to the power of 10 over x cubed. I think we've gone down difficulty again, but that's okay. Is equal to 4. It's nice to have a mix-up of sorts. Alright, so we have the letter of interest trapped within the log function, so we're just going to exponentiate to free this x value. So this is again base e to the power of 4 is equal to the argument. So base e to the power of 4 equals log argument. That's pretty nice. We're going to do the old swap strat, so swap those two. It's not a formal vernacular, by the way. Swapping this one with this one. It's just mathematically true if you do the manipulations. So there we go. And then, of course, using exponential rules, we have base e to the power of 10, base e to the power of 4. So subtract the exponents as the algorithm. So we have x cubed is equal to e to the power of 6, and we will take cubic root of both sides. So no plus and minus shenanigans to worry about because this is odd, undoing the odd to produce odd exponents. So no plus or minuses. So we just have this one. E, what's the cubic root of 6? 6 divided by 3, it's 2. Oh, there we go. Answer. We are good to go. Can back plug it in, please. Back plug. So we get e to the power of 6, and then we simplify to e to the power of 4. Exponential slammage. 4 times 1 is indeed 4. So that confirms the answer. Good to go. Alright, and next up we have a log. Again, log base 10 of e. Don't call this log, please. So that's going to be log base 10 of e times kind of a nasty looking log base x plus 8. Of 125. This looks kind of weird. And then minus log base 10 of e cubed. I'm going to put in parentheses just for good form. This one I'll put in parentheses as well. That is all equal to 0. There's our problem. Taking a survey, of course, this is log base 10. That is log base 10. Those two are matched up, but this is may or may not be log base 10. It's log base x plus 8. So let's make no assumptions and assume that they are mismatched. Wonderful. So let's just start to separate the two different log types. We will keep this on one side and we will move log base 10s to the other side. So let us add this to both sides. So plus log base 10 of e cubed to left hand side, and then we will do the same to the right hand side. That will cancel with that, of course, because that was our intention. And let's cheat a little bit by copy pasting. Alright, so we're gonna look on the left hand side, we have that left over. And on the right hand side, we have successfully moved log base 10 of e cubed to that side. Okay. And as stated before, the strat is just to get the log bases together. This is log base 10. We will move it to that side by dividing it from both sides. So divide by log base 10 of e, divide by log base 10 of e. Those two will cancel as expected, leaving us just that one. So log base awkward x plus 8 of what? 125. And that is equal to wonderful change of base situation, right? This is log base 10. This is log base 10. So we can transform this one into, this is the argument on the top, this is on the bottom, so that becomes the subscript. So it becomes natural log of, because again, the base b, I'm sorry, the base, the argument of the base becomes the subscript. So it's technically like that, but you don't write it like that. So invisible number, and then the argument on top. That's what we get. So using change of base rules, we change it from base 10 to natural log with the base e. Recognize that situation. We could do exponential slammage as well. So take the 3, slam dunk it. That's a coefficient, and this one transforms into just 1. Copy paste the left hand side. Literally copy paste. There we go. Alright, and now we could just exponentiate this one to the power of that equals that. So you could do again this one. Power of that one. And of course, this takes us to a classic situation we've already encountered in the exponents. This is 5 to the power of 3. We have successfully matched the exponents. And thankfully, we have odd exponents, so we don't need to worry about plus or minuses. So therefore, if you just simply take the cubic root of both sides, so cubic root left-hand side, cubic root right-hand side, 5 is equal to x plus 8. And then we subtract 8 from both sides, so x is equal to negative 3. Final answer, but make sure you check for extraneous. If we plug in negative 3 into there, that becomes positive 5 as a base. That is okay. And I think there are no other x inputs. Yeah, that's it. So this is a good answer. Alright, that finishes that piece of paper with pre-written problems. And I think I only have one more pre-written problem. So that should be the last one for today. It's just more of the same thing, honestly. I was running out of ideas or problems. So we have natural log of 3 times log base 3 of x. Already we have mismatched bases. That is equal to natural log of 27 minus natural log of 3 times log base 3 of 4x minus 3. Okay, so survey. We have log base, natural log, log base 3, and log base 3. And we have multiplication right here. It's worth mentioning that we don't have an algorithm for combining stuff like this together. So, what do we do? Well, since we have log base 3 log of 3 times a thing, and then we have a log of 3 times a thing, we should probably get rid of that to free up the log base 3 terms, right? So in effect, this is similar to 3 times x, and this is like a 3 times an x thingy. It's like an x cubed or something. And this is just a constant, like a 27, for example. So if we're doing a problem like this, right? You have a 3x here, you have a 3x here. You should probably just simplify the 3 from all terms. So that's what we're going to do. We're going to divide all terms, or we are multiplying 1 over natural log of 3 to all terms. So term number 1, term number 2, and term number 3. We shall distribute through that, on that, and to that. Thereby getting, this one negates that one, so we're just left with log base 3 of x. That one to that one doesn't simplify perfectly yet. So it is worth mentioning here as well. Unfortunately, this thing right here, it does not become natural log of 9. We don't have an algorithm like that. That's not one of the rules that we possess. It feels tempting to do it, but we don't have that rule, so please don't do that. The only algorithm we have for this one is change of base, which is why we're doing it. So this natural log base matches this one, so we can apply change of base rule, and you see the 3's on the bottom? Of course, it's going to match up. Alright, so again, this one distributes to the last term, canceling with that one. So it's going to be minus, again, this one is canceled with that one. So leaves with just natural log base 3 of that thing. There we go. So again, ripe candidate for change of base. The 3 is on the bottom, so it will become the base 3. Why is that nice? Because it matches the other two bases. Log base 3 of 27. Again, just change of base rule. Alright, let's copy paste the rest of this, because I don't want to save some efforts. Perks of the digital medium. Ah, this is a little scuffed, but salvageable. Alright, put it right here. It's so buggy. I'm right there. Okay. So now things are a lot cleaner. But again, we cannot cancel log base 3 from all terms because this is 1 term, 2 terms, 3 terms. We need to first consolidate those ones, which we can because we have an algorithm for this one. There's a subtraction between term number 1 with base 3 and term number 2 with base 3. So we do have an algorithm, so we can do a quotient of those two. Thereby getting 4x minus 3 quotient. That's the argument for what? Log base 3. Is equal to this one. Copy paste the left hand side. I'll just rewrite it. Okay, so now we can, since we have log base 3, this is 1 term and then log base 3, 1 term, no multiplication thing going on. Everything has coefficient 1 at this point, so we can equate the two arguments. So argument number 1 is x. We can equate it with argument number 2. Again, there's a formal step. I'm going to ignore it for this time. Okay, this is the classic Algebra 1 situation. Multiply both sides by 27. And then subtract 4x from both sides, thereby get... Oh, that's weird. 23x is equal to negative 3? What? Well, we got x is equal to negative 3 over 23. That's really weird. I hope I didn't mess up something. Okay, we back-checked the answer, of course. It's a negative answer. So if we have a negative argument in there, it's going to cause domain issues because log functions can't take negative values. So does that mean this is, what is this, extraneous? So therefore no real solutions? So I think that's the answer. I think I messed up the problem creation somewhere along the way. But that's okay. I mean, it doesn't always have to work out. I think the answer was supposed to be positive 3. Yeah, I have the work written in front of me, how I generate the problem. So let me do a quick pass to just see if there have been some weird mistakes somewhere along the way. Well, first let me check to see the problem is written correctly. It's, yes, natural log of 3 times log base 3 of x equals that thing minus that times the rest of it. Yeah, so this problem is written correctly. Just side note, this is not a bad answer, but I feel like maybe it's not supposed to be that because I wrote this with having one real solution on my workspace. So let's double check. We're multiplying both sides by 1 over natural log of 3. Yes, that's correct. Yes, that's correct. And then, yes, that's correct. This one is, we can transform into that one. So this step is correct. And we can combine this one with this one. No sign changes. Yeah, that's correct. Going from here to there. Yeah, that feels correct. And then... Wait. Oh, never mind. I thought I guess I just really messed up writing the problem. Interesting. It's not very reassuring, though. Again, I'm looking at my scratch work for how I rolled up this problem. Yeah, it seems like everything was going swimmingly, and then something got messed up along the way. But I think this problem has reached a satisfying conclusion, but again, I'm just fussing over to making sure I didn't goof up something somewhere along the way. In the end, the problem was supposed to become a quadratic situation where we're supposed to end up with 4x squared minus 3x minus 27 equals 0. That's what we're supposed to end up with. So the square, we have an x squared, but we didn't have the x squared right here, so I think I miscopied it. No, that's written correctly. Yeah, that's interesting. Oh, okay. I see where things went wrong. Okay. I did it backwards. Alright, so scratch all that. Scratch all that. Okay, so I don't know why I did it like this backwards. So it's supposed to be this one going from left to right. So the 27 goes on top, not on the bottom. And this one goes on the bottom, again, from left to right situation. So I don't know why. I think I just drew it funny, but that's just coming up with excuses. Okay, so I guess in summary, this one would be correct. The work is correct if this one had been correct, but it's not. So this step is the wrong step. So let me fix it up. Okay, so I don't know why I did that. I just goofed it up. It's going to be left to right, so this one goes on the top. So 27 is the numerator, and then the denominator is 4x minus 3. Okay, now that we have log base 3 matching log base 3, we can negate that from both sides. So argument number 1 is equal to argument number 2. Yeah. Okay. And of course, this is a fraction. We're going to multiply both sides by 4x minus 3. Thereby getting 4x squared minus 3x is equal to 27. So, setting it up for zero product property, we're going to subtract 27 from both sides. There it is. This should be a factorizable situation. Factors of 4, 4 and 1, 2 and 2. Factors of 27. 27 and 1. Probably not that one. 3 and 9. Probably that one. So checking it real quick. This is a 6. This is an 18. That gives 12. No way to produce 3. 9 times 1. 4 times 3. Yeah, that's correct. So we have a 4x. The 4x has to be multiplied to the 3. And then the 1x has to be multiplied to the 9. 1x to the 9. Two signs are different. The larger of the two magnitudes is negative. That's the larger negative. Smaller positive. Okay, cool. So thus we have two solutions. We have, therefore we have x is equal to, as candidates, negative 9 over 4 and positive 3. We're going to back check real quick. Again, negative arguments ain't going to cut it. We can't have negative arguments for our log functions. So that one is excluded. So only one answer. X is equal to positive 3. Okay, that's a satisfying conclusion. Yeah, that one works out. As a quick inspection. Yes. Okay, cool. Okay, so I think that is it, because I've run out of problems, pre-written problems I mean, until I scrounge up more problems from old problem sheets that I've made up. But for now, I think that's good enough. So I'll probably see you another time. I might do some English later, English grammar later, but we'll see how I feel. I should probably exercise though, stay in shape. So that'll be it. Hope you have a good one. See you next time.